In section 10.2, we're going to cover simplifying radicals. I have 5 examples on the board here, and the first one is kind of a basic square root. A lot of people call this symbol a square root symbol, but it's actually a radical symbol, and we're taking the square root of the number underneath the symbol. The first problem is the square root of 160. Now you can type that in your calculator, and you're going to get a number with a decimal after it. But if we want to simplify it and keep it decimal free, then we need to do a couple of things, or at least know a couple of things before we get started. One is we can break the numbers apart, or we can factor the numbers apart underneath the radical sign. So in this case, I can break 160 apart into 16 times 10. These two factors, then we can separate those as the square root of 16 times the square root of 10. Now from this point, the reason I did that actually was because I know 16 is a perfect square, and I'm looking for perfect squares when I'm factoring underneath the radical sign. So 16 being a perfect square, I know the square root of 16 is 4. So now I have 4 times the square root of 10. Now there are no perfect square factors inside of 10. There is 5 times 2, but neither one of those are perfect squares, so we're going to leave it just the way it is. So the answer will be 4 times the square root of 10. And this is how you simplify just by removing perfect square factors. Our second example, we're going to be removing variable factors. We're also going to be removing factors from our coefficient, but we also have a variable n to the 7th. Now this is similar to example 1, and that we need to find any perfect squares that we have and separate them from the other factors. Well, in this case, 54 can be 9 times 6. 9 is a perfect square. 6 is not a perfect square. Now, n to the 7th, this is a little tricky to think about, but it's pretty easy once you get the idea of it. If I take an even exponent and multiply it times 1 times n to the 1st, then I would have n to the 6th times n to the 1st. That would give me n to the 7th. So if you have an odd exponent, just take 1 off of it and multiply it times that variable to the 1st power. So now n to the 6th is the perfect square, 9 is a perfect square. Why is n to the 6th a perfect square? Well, remember, we add our exponents when we're multiplying variables. So if we're adding them together, we can add 3 plus 3 to get to 6. So when we take the square root of n to the 6th, we just kind of cut it in half. So we're going to separate these. 9n to the 6th times 6n. Now we can take square roots here. Square root of 9 is 3. Square root of n to the 6th is n to the 3rd. Now think about it. N to the 3rd times n to the 3rd is n to the 6th. Remember, we add the exponents when we're multiplying variables. And then still under the radical sign with no perfect squares left is 6n. So we have 3n to the 3rd times the square root of 6n. Our third example, I'm going to show you how to multiply 2 radical expressions. So we have one radical, 2 times the square root of 7x, times 3 times the square root of 14x squared. Now when we do this, to start with, we multiply the 2 numbers outside of the radical sign. It's almost like these are coefficients and the whole radical is kind of like a variable. It's not, but you can kind of think of it as having the same rules when you're multiplying. So we say 2 times 3, which is 6, times, underneath the radical sign, 7 times 14, which is 98, and x times x squared, which is x to the 3rd. Now, that's the answer multiplied. but that's not simplified. We need to simplify it. There are perfect squares underneath the radical sign. Anytime we have perfect squares under the radical sign, we want to take them out. We don't want to leave them under there. It's not simplified if you leave them underneath the radical sign. So the perfect square with for 98, there was a perfect square factor in there, which is 49. So you have 49 times 2, which gives you 98. So 49 times 2. And then x to the third. Remember, I said if you have a odd exponent, just take 1 off of it and separate it. So we have x to the second times x, which gives us x to the third. Now, 49x squared is a perfect square. We can take the square root of that. We can bring that outside of the radical sign. And we'll be left with 2x underneath, because 2 is not a perfect square and neither is x. So we bring it out, we multiply it times the 6. It's because this is 6 times the square root. So when we do that, we're going to have, we bring out a 7, square root of 49 is 7. We'll bring out an x, because the square root of x squared is x. So when we bring out the 7, 7 times 6 is 42. And the square root of x squared is x. And we're left with 42x times the square root of 2x. Yes, those are birds. I hear you. Our fourth example, we're dealing with simplifying fractions within a radical sign. And this is pretty easy, but the fraction is not simplified if there's a fraction underneath the radical sign. There's rules to simplifying radicals. One of them is you can't leave any perfect squares underneath the radical sign. The second thing is you can't have a fraction underneath the radical sign. And the third thing is you can't have a radical sign as your denominator. So you can't have a radical sign in the denominator of a fraction and have it be simplified. So we're going to kind of touch on all three of those things. We already did once, or actually 3 times, where we've eliminated a perfect square from underneath the radical sign. Now what we're going to do is we're going to eliminate this fraction from underneath the radical sign. And what we do is we split the fraction. So the square root of 64 over the square root of 49. And this still means the same thing. All we've done is split it now. Now these are both perfect squares, so you just take the square root of both. So the square root of 64 is 8, and the square root of 49 is 7. So your answer ends up being 8 over 7. This takes us to example 5. And actually example 5, I'm going to do 2 examples that deal with rationalizing denominators. This is the first example, and I'll add the next one when I'm done with this. Rationalizing a denominator. What that technical term means is getting rid of a radical sign in the denominator. Don't have a denominator with a square root symbol down in the denominator. So the way we do that, it can be easy. Sometimes it can be a little bit complex, but for the most part, it's not too bad. Here's what we do. If we want to lose the radical sign in the denominator, we simply multiply this fraction by 1. Now, as you know, 1 can be written an infinite amount of ways. And in this case, we're going to write 1 as the square root of 7 over the square root of 7. Any number divided by itself is 1. So the square root of 7 divided by the square root of 7 is 1. And anytime we multiply a number by 1, it doesn't change that number. So the reason I'm doing that now is because when we multiply the square root of 7 times the square root of 7, we get the square root of 49. Hopefully you see what I'm doing here, but let's do the numerator now. The square root of 3 times the square root of 7 is the square root of 21. Now I have the square root of 21 divided by the square root of 49. The square root of 49 is a perfect square. That means we can simplify that, and we have the square root of 21 divided by the square root of 49, which is 7. So watch what we did again. We noticed that we had a denominator that had a radical sign. So in order to eliminate the radical sign, we multiplied that fraction by the denominator divided by itself. That eliminated the radical sign. It also changed our numerator. That's a basic one. Now I'd like to show you the next part of this example, which is a little more complex, and I'll put a variable in the problem. Example 5b, we're going to be doing something similar that we did in example 5a. We're going to be rationalizing the denominator in this fraction. But in this fraction, it's a little different because this fraction, as a denominator, we have the square root of 8n. Well, 8n can be simplified before we rationalize the denominator. If you notice, 8n has a factor of 4 times 2 times n. And that 4 is a perfect square. So we can factor out the square root of 4, which is 2, and we have a new denominator. Square root of 4 is 2, and then we're left with 2n underneath the radical sign. That doesn't solve everything. We still need to rationalize the denominator. The denominator cannot have a radical sign in it in order for it to be simplified. So just like example A, now we can multiply this fraction by 2n divided by, the square root of 2n divided by the square root of 2n. This is so that we can get rid of this radical sign. Now, what we end up having is the square root of 2n times the square root of 2n. That answer is just 2n. So we have 2 times 2n. And in the numerator we have the square root of 7 times the square root of 2n, which is the square root of 14n. Now the last thing we need to do is simplify our our denominator. And 2 times 2n is 4n. So to go over that one more time, the first thing we're going to do is simplify and factor out 8n to 4 times 2n. Then we take the square root of this perfect square 4, bring it outside of the radical sign. The square root of 4 is 2. And we're left with the square root of 2n. Then to rationalize the denominator, we multiply by this number in the numerator and the denominator. The denominator, when you multiply those two, it eliminates the radical sign because we get the square root of 4n squared. Well, the square root of 4n squared is just 2n. So we have 2 times 2n, which gives us 4n. The numerator is the square root of 7 times the square root of 2n, which gives us the square root of 14n.